I wrote this presentation in the first place was because I've just written a book on the same topic. So this is Reinforcement Learning by O'Reilly, and the reason why I wanted to create this book in the first place was that I was really inspired by a lot of the research that was coming out of academia and some of the applications that they were able to achieve using reinforcement learning. But I saw and I noticed that many of those advancements hadn't really made it into industry yet. So the goal of this book really is to attempt to gap or span the gap that exists between academia and industry. I've tried to take a lot of research as much as I can, put it into a book that's accessible to engineers that are practicing, engineers within industry. And hopefully you'll enjoy the book and you'll learn a lot more about how reinforcement can be used. So this is a presentation that spins off this book. It concentrates a lot more on the applications of reinforcement learning, and I've got a few videos and demos that I'm going to show to just provide some of those examples. But before we get started, the first question is always, what is reinforcement learning? So I'm just going to attempt to pause the video here. I've forgotten my shortcut keys, not that one. Okay, is it space? It's not space either. Okay, I'm going to have to attempt to use the button instead. So this is a video from a couple of researchers who are attempting to train a chicken to do tasks. Chickens, I have some chickens in my garden. We have some pet chickens that are principally working animals. They produce eggs, but at the moment it's cold, it's winter, and they're not laying any eggs anymore. So they're just lazy freeloaders, eating my food and not doing anything to earn their keep. But give it a couple of months and they'll start laying again, and all will be good. But chickens are actually remarkably intelligent for a bird that is principally considered, to be pretty unintelligent. But actually, you can train them to do quite complex tasks. People think of birds like parrots and things to be really intelligent, and crows and things like that. But actually, chickens have a pretty good amount of intelligence to do some complex tasks as well. So in this particular video, I'm going to try and pause it so that it looks okay on the video stream for you guys. But what the researchers are trying to do is they're trying to train the chicken to tap a particular dot. So every time that this chicken pecks at the pink dot that is on the table there, they're going to reward that chicken with some food, with a tasty treat. And over time, they're adding more and more circles to make the task more complex. So the chicken here is having to actively look for a pink circle that exists on the table and compare it against other circles that have similar colors or similar shades. It's interesting that chickens see in full color, unlike some other animals that only see in black and white. Chickens see in full color, so they are able to pick out the differences between the different colors. But you can train the chicken to do this task by providing some positive reinforcement. So every time it does something right, it will get some food. Every time it does something wrong, and I think I've just paused it in the right place, because the researcher on the left there, she moved the pink dot away, and when the chicken turned around, it expected the pink dot to be in the same place where it was before. So it's instinctively started to dip down and try and get to the pink dot, only to realize that actually it's pecked in the wrong place. And in that particular instance, it will not be rewarded. It will not get a positive reward from that action. And instead, it needs to try again. Wrong button again. Sorry about this. So that food that is being provided there is the act of reinforcing a behavior that we want the chicken to learn. And this, in essence, is what reinforcement learning is. We're attempting to train an agent, which is in this case a chicken, to perform behaviors or enact strategies, and we teach the agent to do that by providing a reinforcing signal. It can be positive or it can be negative. Both tend to work reasonably well. Okay, so that's all well and good. So how far can we take this? How smart are birds in general? Well, a long time ago, this is some research from Skinner, I believe, and he trained. So this was, just to give some context, I definitely clicked the pause button there. Definitely clicked the pause button. Damn you for clicking. There we go. This was during the time when pigeons were being used for all sorts of tasks. Carrier pigeons were still being regularly used for communication, and pigeons were being trained to spot submarines during wartime and things like that. So this was kind of part of the same era of research, and he found that he could train pigeons to also read. Again, the way in which you would do this is you present some input, some stimulus to the bird. In this sense, it's a sign here at the top right that says peck. And if and when the bird actually performs that action, then a little treat is delivered through the slot below. And over time, he managed to build up quite a repertoire. We've got peck there, we've got turn, telling the pigeon to turn around, gets a little treat, positive reinforcement. Turn again. Okay, so these are pretty advanced behaviors. So how far can we take this? I found this clip on YouTube and it's amazing. This is a guy that has trained his chicken to do all sorts of feats. I love his t-shirt. It says, my chicken is more intelligent than your dog. And he's, in this time of nationalism, he's trained his chicken to be a nationalist, and he's trained his chicken to recognize the Spanish flag. So as you can see, he's ignoring the French flag there, ignoring the Swiss flag, because the Spanish flag is definitely the flag that's most interesting to that chicken. And we've also got this extreme example of patriotism here. If and when chickens do take over the world, they're going to be able to raise their own chicken flag. And all of these behaviors were all trained through reinforcement. Okay, so this is the general gist. We're trying to train the agent, which is a chicken. Oh, and she loves it. Trying to train the agent to do complex tasks, and all the chicken lovers love it there, to perform complex tasks through reinforcement. So let's step back a little bit, and how can we apply this to industry, and why is it of interest to engineers that work in industry? I think we need to step back and establish where reinforcement learning sits as a tool. Like when would we use it? Because this is just another set of tools that we can use to solve problems. So in terms of a day-to-day business, there's kind of three levels, or very simplistically, there's three levels of business that happens on a day-to-day basis. Businesses enact processes, things like printing forms, sending mail, informing customers, speaking to people, providing their product, things like that. Also, businesses make decisions. So these tend to happen less often than processes underneath, but they tend to be more important. So decisions like, are we going to give a loan to this person, or what product should we build next, or so on and so on. And finally, at the top level, we've got strategy. Strategic businesses attempt to map out long-term goals for the business, ultimately to build a successful business. Now, strategic decisions happen rarely at all, but the strategic decisions are really important because they inform and control and direct the decisions that are going on at the lower level, and finally the processes at the bottom level. Now, the value of each of these actions, because of the nature of what they do within a business, are quite different. Processes like how to connect your laptop to the works printer, it's a process and it's important, but it's not very valuable to the business. Decisions are quite valuable because if you are about to give someone a mortgage, then you could potentially lose a lot of money if they don't pay that money back, or you could make some money similarly. And finally, strategic actions tend to be the most valuable because they're the ones that help define what success is. They're the things that can really make a business, and therefore they are the most valuable. Get them wrong and your business fails. It's the ultimate. It's the ultimate in the value chain in a business. And over time, we've developed tools and techniques and technologies to automate these parts of the business. So we use software to encode business processes. We've been doing that for a long time, and there is value in that. And obviously there's a big industry supporting that to build and write software to encode and define these processes. I see ML kind of at the level where you are attempting to automate decisions. So we can train a model to make a decision as to whether that person would be accepted on that loan or not, based upon previous data, things like that. So that automates the decision. Now, RL, that is the thing that sits on the top. That is the thing that defines the strategy. We can use RL to help optimize strategies. So basically longer term thinking, things that take sequential decisions over time, that's where RL fits in the stack. So it's my opinion that RL is very valuable, but you've also got to bear in mind that actually these strategic decisions don't happen that often. So probably the market is a bit smaller, in the same way that, you know, the ML market is quite big, but the software market is bigger because there's just more users of software than there are of ML. And similarly, there are more users of ML than there are of RL. But still, it represents a tool that you can use, something that you need in your toolbox to be able to solve those specific strategic long-term problems. Sorry. Okay, so what do I need in order to do RL? I've already mentioned some of these terms a little bit already when I was showing you the videos. The first one is the agent, this thing at the bottom. The agent is the thing that actually builds the internal model to solve a task. And in the previous video, it was the chicken or the bird. If you imagine trying to teach your children to ride a bike, then the child would be the agent, and the child is cycling within an environment. The environment here is the world. It's the sensation of wind on the face. It's the view of the trees and the grass on the floor. It's the it's the feeling. It's the feeling of acceleration and enjoyment and pain when they fall off. Okay, so it's everything, all of the representation of the outside world, everything that is external to the agent is the environment in which the agent acts within. Okay, the agent is able to select from a certain number of actions. These actions might be, in the cycling case, might be to turn the handlebars to go left or right, might be to pedal forwards and apply some power to the pedals. It might be an action to shout, hey dad, look at me. And all of those affect the environment in some way. They mutate the environment. So if I turn around 180 degrees by turning the steering wheel, then the environment's going to change. I'm going to have a different view. I'm going to be able to see something different. I might be feeling different things. I might be hearing different things. So the actions provided by the agent mutate the environment. Then the environment also needs to feed that information back to the agent in some way. So that's called the state or the observation of the state. And this could be like a visual data, like a camera or something from your eyes or your ears. In the chicken example, when the researchers were moving the dots around to train the chicken, the state could be potentially the positions of those dots or a picture of those dots. That would be a representation of the state of the environment. And obviously, when you're going around in this loop, you're enacting, you are performing actions to mutate the environment. So that actually changes the state. And then again, the agent will then look at that state and suggest another action. And this goes round and round and round and round and round and round. There's one final thing, though, that's really important, and that's the reward. This is the thing that tells the agent that you've done something right or you've done something wrong and you need to change your model. If you've done something right, then it's reinforcing that model. It's saying that was great, keep doing it. In the cycling example, the reward could be, the pleasure from cycling or of the freedom that you get from cycling, or it could be the pain from falling off your bike. And remarkably, but both of my kids now, my youngest is 4. I think they both learned at about 4. It's about 4 or 5, but at the age of 4 or 5, they were fully capable of pretty much learning how to ride a bike entirely by themselves. You give them support and a little push and stuff, but at some point it just kind of clicks. They get the right model in their head. They know exactly what happens with the bike, and away they go. Okay, so it's a remarkably simple, framework, I guess. It's a remarkably simple framework, but it can result in really complex behavior. Oh, I thought there was a video there, but there's one video that, is it later on? Yeah, it's not. Okay, there was one video that I really like where there was a chap who took a bike and he reversed the steering on his bike. And so if you, so typically if you turn the handlebars, like, pull with your left hand, it turns the wheel to the left. Basically, you put a cog on there so that when you pulled with the left hand, the wheel actually went right. And it was a really good experiment because it's remarkably difficult to adapt to such a simple change. Like, it's just such a simple change, but the models that you've produced when you were 4 or 5 year old to ride a bike are so deeply embedded within your head that it can be really hard to bring yourself back out and basically say, I have to relearn how to ride a bike. And it is possible, and he did do it, but it just took a certain period of time. But conversely, when he gave that to his son was able to get it in 20 minutes or something, and it was away. So anyway, a bit of an aside there. And so the purpose of this talk now, I hope you gained something from that. Obviously, there's a lot more detail about this. This is called the Markov decision process, and MDP is the mathematical name for it. There's a lot more about this in the book, so if you're interested in the details, then I refer you to the book. But as part of writing this book, I was really interested in the applications. I really wanted to collect and talk about some of the use cases that people have tried, that people have succeeded in, and less often failed in, which is a problem with academic research and research in general. You don't hear about the failures. But it was remarkable, and what I found, the spectrum of ideas and things that people have tried was surprising. And so I started to collate all of this information. I started to categorize it and keep it, and I've put it on the website for everybody else to have a look through. So if you're interested in finding applications in your specific domain, then I suggest you go to rlbook.com/applications. I'll just go to the rlbook.com website, and you'll find a link at the top, and you'll be presented with a big selection of use cases for your particular domain. So I'm going to talk about a few of those now. I think I've got 3 different sort of distinct industries that I'd like to talk about. The first one is manufacturing, and in manufacturing, there's lots of sub-use cases that are also interesting. So for example, like supply chain management, inventory control, these are pretty big applications within manufacturing. But one of the coolest applications and the most visual is robotics. Okay, so I'm going to start off with a couple of examples, and you make of it what you will. So this is a really interesting video of some research that people did to take an off-the-shelf robot, which I can't remember who makes this robot now, but it's a robot that you can buy off the shelf. And that robot comes with a predefined set of moves that it can perform to do certain tasks. So for example, it comes with a pre-built set of algorithms to walk forward, to turn left, to turn right, walk backward, things like that. What these researchers were interested in doing was to see if they could look at a real life animal with a similar that has a similar what am I trying to say? Basically, they wanted to find out if they could look at a dog and use motion capture to capture the movements of a dog, and then try and train the robot to mimic the actions of the dog. And so over time, they managed to train all sorts of more complex behaviors, like a backwards trot, for example, or side steps. And all of these behaviors were not available, are not available off the shelf, okay? Because some of these behaviors are really quite complex, and they're very hard to encode. So in fact, you need to learn these behaviors. We've got some sort of complex turns there. This is one of the coolest ones. So this is like a 90-degree like hop jump. And this is incredibly difficult to program because of the complexity of the movements involved. I'm going to try and pause it just so you can see some of the joints and how they move. So you can see here that there's the joints are kind of moving in opposition, and the way in which they're bending and putting strain on the motors is something that would be very, very difficult to hand code. I mean, I just have a go trying to hand code some robotic movements. It's actually remarkably difficult, but you can use RL to train an algorithm to produce these behaviors based upon some motion capture footage of a real animal. Okay, so then they go into the details of how they trained it. All right, but that's cool. You can check out that example if you're interested. Next one. This might seem a slightly more boring example, but actually this is really fascinating. I'll explain why in a minute. So what we've got here is we've got a couple of sort of articulated arms. You see the servo motors here, they're all connected together with a little sort of manipulator thing on the end. And the goal of this challenge is to rotate that imaginary valve to a predefined position. Sounds simple enough, and it sounds like it doesn't really have a real life application, but it does. Like I've worked with the oil and gas industry quite a lot, and they have a lot of applications where they simply need to turn valves to an off position or an on position, and they've got no way of doing that other than doing it by hand. So they actually have robots that can be driven up to these things and attempt to spin them. So I mean, it is a real life use case. But the problem is these valves are all different size and shapes and looks and feels. Some have got handles, some are like round, like steering wheels, and some are just bars, etc., etc. So again, it's ridiculously hard to try and program a robot to do this from hard-coded rules. So what you can do is learn how to do it with reinforcement learning. The particularly cool thing about this application is that the only thing that is being used to train this robot is this video camera. This is the only thing that these arms are actually using as their state, using as their input. And over time, it is learning to position this valve in a very particular way, purely from the video camera. So actually, the coolest thing about this research is not necessarily the application, it's the fact that you can train a very complicated, articulated robot with just a video camera. So that opens up a whole range of applications, and one in which we're going to, I'll leave that for a second, I'll show this one first. And one which leads me to this. So this is actually a real life pick and place robot in Berlin. And earlier this year, a company called, I've put my video over the top of the source there. The Covariant AI is the company that did this. And yeah, they've used reinforcement learning to train a robot to pick up any object. You see, let me try and see if I can pause it. There we go. So there's just some white boxes. There's some orange boxes, small boxes, thin boxes. And we've got anything more interesting than that. I saw a roll of tape, oh, look at that. So that's like a plastic bag with some sort of plastic shapes inside. All of these things are completely different shapes. And again, it would be very hard to manually hard code a way of telling a robot to pick up an individual item with a simple manipulator or even a complex manipulator. But using reinforcement learning, it is possible. And again, you can use, for example, a video camera as the input to this. I believe it's got several cameras on this robot, and you can use that information to train the robot to do certain tasks. Okay, so in the past, one of the main problems with reinforcement learning was getting the information to the agent that is representative of the problem at hand, and then processing it in an efficient way. But the confluence of the advancement of neural network based models and computer vision and things, paired with the advancements in reinforcement learning and the techniques and the models, put these two things together, then we can get some quite complex applications. So let me go back, because this one's really fun. One thing that's really, there's a whole range of robotic examples out there, and they're all really cool. But I like this one because this is demonstrating something that's seen in other parts of ML, and that's adversarial training and adversarial attempts to break models. So what's happening here, this is just a simulation, but the simulation has included a model, quite a complex model of a human being. So there's lots of, imagine this to be a humanoid robot, lots of joints, lots of movements, and it's been trained to kick a ball. And so it can kick a ball, try and score a goal. The blue robot, sorry, what happens if I just click? I could just click in the middle. So the blue robot has been trained to score a goal. So it's going to try and move and wiggle across and try and score in the goal. So when it does score a goal, it gets positively reinforced. When it doesn't score a goal, it gets a negative reward. You see the red robot in the goal there, that's trained to try and save the goal. So again, it's trying to, it gets rewarded when the ball doesn't go in the net, and penalized when it does. But what they found is that after this training, if you then, you can then adversarially attack one of the models, in this case, the RL agent that is blue robot here, you can adversarially attack that model by presenting it with data and presenting it with information that it has not seen before. So in this case, it's learned that if it just falls on the floor and just flails about a little bit, the blue robot doesn't really know what to do because it's never seen this before. So in fact, it just looks a bit drunk now, stumbles off to the right, and it can't even kick the ball. It just falls over because it's never observed this before. So it's never learned to deal with this scenario, and it just about managed to cope with it there, but it's certainly more drunk than it was before. So, again, this is all based upon ML. A lot of these models are neural network based. A lot of the same caveats apply. I'll just leave it there. Okay, so let's move on to a different industry. So the tech industry is a big user, well, it's not a big user yet, but it certainly could be a big user in the future. One of the coolest examples that I came across was the automation of common office-based technology tasks. And in this case, the researchers created a framework that allowed you to present an agent with a HTML-styled application. And in this case, it was a simple email application. And the researchers wanted to try and train an agent to be able to perform relatively complex tasks. Things like, taking some text or a command and saying, please forward Kyle's email to Alice. And, throughout a whole range of these scenarios, the agent was trained to perform these commands. And this is an example of forwarding one of the emails. And you can see that there's a series of steps that the agent would need to go through. Each of the boxes at the top represent the state. So this state is represented by HTML and just text. The actions the actions presented to the agent were things like CSS selectors. So it's like select a certain HTML element, or copy a certain piece of text, things like that. And as you perform these actions, you get into different states. So in order to forward the email from Bob, the agent first needs to learn to click on the email from Bob, and then it needs to learn to click on the forward button at the bottom, and then it needs to learn to type the word Alice in the to box, and finally hit the send button at the top right. Okay, so that's like a full end-to-end chain. And this may not render in your video, I hope it does. But basically, this is a visualization of the agent learning in real time. And this is kind of at the end of the process where it's got a pretty good model, and it is able to do really quite complex things like, click an email and forward it to a particular person, or delete a certain email, or reply to someone with some text there. In the yellow box, you can see the command that is being presented to the agent, and they're pretty complex. Forward all mail from Patricia to Ginger. Tell Anita some Latin I'm not going to pronounce. Freddie needs an email, blah, blah, blah. Find Kirby's email and say something. Highlight, so on and so on. This is really complex, but this has potential to provide a level of automation in sort of traditional office-based technical tasks that I don't think has been seen before. And even though this is like simplified HTML, obviously, I feel like that there's just a use case that is just waiting to be discovered to use this technology on. And when they do, I'm sure it's going to be really successful, and it's going to be really popular. So get your thinking caps on, everybody, and then tell me. Okay, moving on to transport. This is the final one now, so not long to go. This is a quick sort of wrap-up video, really, showing lots of different applications. One of the main applications that has been tackled in transport is traffic management. It's specifically, given a busy road, how can we manage it in such a way to optimize for efficient flow and max speed and no delays and things like that. So these are just some videos of examples of various frameworks using reinforcement learning to train how to manage these things. And I'm going to just pause it in a second. Here we go. So what we've got here is a really complex simulation of merging roads, and this is really cool. This is a really cool application. Basically, what the researchers did was they assumed, and this isn't, well, I'll get into the assumptions in a minute. They assumed that you had a motorway or a highway that you are able to tell drivers to set their cars at a certain speed. All right, so you can imagine that maybe these are autonomous vehicles, and there's a direct command. You must travel at 30 miles an hour or whatever. Or it could be like a human. There could be signs above the road that enforce speed limits for individual cars. It's not infeasible, but it's still a bit of a leap there, a bit of an assumption. But the cool thing is that you can use reinforcement learning to learn over time how to tell these vehicles to travel at a very a specific speed, so that later on down the road, a merging lane can simply just pull in. It can pull in, and it can be guaranteed that there's no car in. There's no crashes, and the merge is perfect. Nobody needs to slow down. Nobody needs to speed up. Nobody needs to check. You just merge. Okay. So I feel like that this particular example is like, it's on the cusp of being possible, like not quite there yet, just because of the underlying infrastructure that would be required to do this. But I feel like we're not a million miles away. And, if we were to do something like this, then, that would be the end of traffic jams, effectively. No more traffic jams, because you can, a long way back, you can tell vehicles to travel at a very specific speed so that they never have to stop. And I personally can't wait for that to happen because I hate sitting in traffic. It's the worst thing ever. Okay, I'm not sure what time it is, but I think I've probably used up all my time. I'm going to just stop there, and I'd just like to forward you to the book. So the book goes into a lot more detail. It talks a lot more about the algorithms and how you can actually use some of these algorithms. There's still quite a few applications in there as well. If you are actively working on a reinforcement learning project in your company right now, then I really, really would love to speak to you. I want to, hear about what you're doing and whether you need help doing that. And if you do need help, then yeah, my consultancy, winderresearch.com, is here to help. And yeah, that's it. I'll answer any questions after we finished. Thanks a lot.
Thanks. I shared the link to the book site. It's in the chat in YouTube, and also you can find Phil in Data Talks Club Slack. Yeah, so we do have a couple of questions.
Yeah.
Michael is asking, could you elaborate on the reasons to see reinforcement learning chiefly at the strategic level? Many use cases, for example, in robotics, don't seem strategic to me.
So I was just getting my my speaker volume back up again. Can you just repeat the question again? Sorry.
Yes, sure. So the essence of the question is the examples that you showed. do not always seem strategic. Yet at the beginning you showed this pyramid, and the reinforcement learning was at the top, right?
Yeah.
So and the question is, why do you think it is strategic? Because most of these cases, they don't seem strategic.
Yeah, okay. So it's basically the definition of what is a decision and how many decisions need to be made over time. So a strategy is basically a set of rules that allow you to make multiple decisions over a long period of time. That's the definition of a strategy. In reinforcement learning, the technical term is policy, but I actually find the word policy a little bit, hard to understand. So I tend to use the word strategy because it kind of maps to what we think as of the word strategy. Whereas, like, conversely, a decision, an ML algorithm will make a single decision at a single point in time. So, for example, imagine you're an e-commerce company and you're trying to optimize your advertising or your recommendations so that people buy more stuff. A current and typical ML setup would be to optimize for the highest chance of that person buying the product right at that time. Basically, you want them to click the buy button right now, even though in the long run, it might not be the best decision to actually sell them that product. Actually, a slightly better example would be the recommendation of like news stories or articles or something. If you go for the most clickbaity news article, yes, you'll probably get the click there and then. But actually, the long-term retention of that user is probably going to be affected because they're going to say like, well, I'm not going to use this service anymore because they keep recommending these real clickbaity, horrible articles, and I'm not going to do it. So when I say strategy, what I mean is a strategy is something where you're optimizing for decisions over a period of time, over multiple decisions. So for robotics, for example, it doesn't look strategic in the business sense, but it's very strategic because a decision to move from point A to point B is part of a longer strategy to make a cup of coffee or to pick and place something from one box to another. You can't do that with ML. Does that make sense?
Yeah, it does. Thank you.
Great.
Then we have a question. So thanks for the great talk. Yeah, thank you indeed. How can RL agents be trained well for strategic decisions as they occur so rarely?
Yeah, that's it. That is actually a really good question. That's one of the trickiest problems in RL, and you'll find that you need to rely on simulations a lot more. So during the development cycle, you're trying to figure out like what's the best way in solving this thing. You're iterating over algorithms, you're iterating over ways of feature engineering and things like that. And the best way to do that is through a simulation. So there's a lot of work gone into some very sophisticated simulators for certain domains. Like the most obvious one is the 3D world simulations and renderers, the unities of the world. They've put a lot of effort into making it like physically to put the physics in the simulation so that when you take it out of the simulation, it's as representative as possible. However, that's not the only solution. That just helps you with the development. The next solution is that there's a whole branch and there's a whole box of new techniques that allow you to take historical data and use that to train a reinforcement learning model. It's called offline learning. So although they may not happen frequently, they probably have occurred many times in the past. So you can leverage that information to train your agent to basically not start from zero. You can start from a much better position. So yeah, basically the combination of better simulation and also offline logs, I think partially solves the cold start kind of problem.
This is how AlphaGo was trained, right? So first they looked at the logs at previous games.
Yeah, right? That's a little bit different though, because the the environment was so simple. It's a game, you know, it's got very fixed rules and it's got a very low dimensional space to operate in. So they can physically simulate every single possible move that would ever happen in a game. So in that case, you effectively just need to run the simulation enough times, and then eventually you've kind of seen every possible thing that could happen with it. I know there's lots of permutations and stuff, but you can physically do it. Like now extrapolate that up to like a self-driving car. Like you can't possibly see every single situation that a self-driving car would ever see in a simulation, because life is just too complex. So in that case, yes, you can learn from the simulation, but you really do have to actually get out in the world and actually experience things to generate the data to be able to train a better model. And that's exactly what all the big self-driving car companies are doing right now, where they're just collecting huge amounts of data in order to try and, you know, cover as many cases as they possibly can.
Yeah, I think these companies, self-driving companies, they have like even replicas of real cities, right? So that the car can drive there and learn. Right?
Yeah, exactly. Yeah, I know. Yeah, I mean, it's crazy the extent they have to go to, but even then, that's still not enough. You know, you still need to go to India and attempt to drive a car in India, then you're definitely going to see. Figure out. I think it would just get stuck. It wouldn't move because there's just so much chaos going on around it.
Okay, then we have a question from Razona. Can you sketch a list like here are the things you should minimally have in your use case for reinforcement learning to be applicable? Like what are the things?
Yeah. Okay. Good question. Let me try and. So the real thing that is, I think, the most difficult thing to get your head around when you're doing reinforcement learning is that you have to accept that the algorithm and the agent, the algorithm inside the agent, actually has the capability and the mandate to try whatever action it wants to try. You can't, I mean, so there's a lot of work on safe RL, by the way. The big caveat there, you can constrain and control and make RL safe, but somehow, like, letting go of, we're so used to doing supervised machine learning that, you know, it's under our control. It's quite a leap then to go to reinforcement learning to say that actually the agent needs to do its own exploration to figure out what the best strategies are, and there may not be what you expect. There may be something completely different. So I think that's the first thing, is you've got to kind of get your head around that. But then after that, it's just basically solving the MDP. What's the agent, you know, what's actually doing, what is generating the actions, what actions can it generate, what environment is it working in, what is the state and the observation that comes back from the environment, and then finally, how do you encode and decide upon the reward that comes back from the environment. And actually, out of all of that work, it tends to be the observation of the state. There's a lot of feature engineering that goes into that step, and also the definition of the reward. That can really trip you up, because you can think that you're rewarding the best behaviors, but in fact it promotes bad behaviors. So again, you need to go through a lot of it. Well, I guess you call it reward engineering, in order to figure out what the best reward is. Slightly
definitely not an easy thing to do, right?
No, it's not simple, but it's doable.
Okay. Then another question from Razona. For both examples just given in CRM, it's hard to track these people. They visit website once and then 3 months later they sign up. How would reinforcement learning help?
Yeah, I mean, that's a perpetual problem. Like marketing, they want information, about as much information about the person that's visiting their website as they can, but they're no longer allowed to capture that information from from any other means than the information that's provided by the person. So I think the problem lies elsewhere. That's not a reinforcement learning problem. That's a data collection problem. In terms of reinforcement learning, you know, the goal here isn't to convert someone from well, I guess it is. Reinforcement learning in that case would help, I think, in the traditional testing of different parts of the the website or the workflow in order to optimize to, improve customer sales. So the classic technology at the moment is kind of A/B testing. Now that's the simplest version. Then there's multi-arm bandits, which is like a level above that. And that is actually a simple form of reinforcement learning, by the way. Multi-arm bandits are kind of considered to be part of the reinforcement learning bandwagon. And then you can keep going up with more sophisticated algorithms that are able to learn more complex and more complex behaviors and deal with more complex actions and states. So I think that's kind of the thing that jumps off the top of my head. You can imagine a situation where, yes, you've only seen the customer once, and yes, they come back 3 months later to purchase something. But in the meantime, you can tinker with the whole website. You can get an RL algorithm to generate new text, to change different colors, you imagine every single person that visits that website might be viewing a different version of that website. Things have moved around and they're reading different things. And even though there's only 2 touch points there, with enough customers and enough data effectively, you should be able to tell like what, or the model, the agent rather, should be able to tell which works the best for your product and your company.
And multi-arm bandits are probably the most widely used method of reinforcement learning.
Exactly, yeah.
So the next question we have is strategic sequential decisions cannot be simulated in some cases, like real world strategic decisions that impair huge risks.
Yeah.
Can it still be achieved?
Yeah. It depends. It depends on how not possible it is. Like I've worked in several industries where it is very expensive to perform experiments, and so you can do them. You just need to orchestrate them in such a way to make them as cost effective and as short as possible. If it's a safety thing, then again, you can generally figure out ways of testing up to the point where it becomes unsafe. And there's the whole branch of RL called safe RL, safety driven RL, which attempts to provide ways and means of making RL algorithms safe. So if that's your concern, simulations are a massive help here. Simulations can be created that are so sophisticated that they're almost like real life. So simulations can really help. But yeah, you're right. Sometimes there's just certain things that can't be tested in real life. And, similarly, there's in ML, there is maybe certain applications where it's just impossible to get the data. And in those cases, there's probably just lower hanging fruit. There's probably simpler problems that you can tackle that can be solved. So I would probably just consider changing the problem definition.
Mm-hmm. Okay, thank you. What is, in your opinion, the current bottlenecks of expanding applications of reinforcement learning to more tasks and fields, like development of algorithms, hardware, and etc.?
Yeah, good question. So I think that the hardware is probably good enough for many use cases. I think, to be honest, I think there's maybe just a lack of awareness at the moment, and that's exactly why I wrote the book, to try and increase awareness in this area. I think that many engineers have just not heard of it before. It's still considered a very academic subject. So give it a few more years, and I think that once people start hearing the word, they'll potentially start using it more. I think inherently there's a narrowing of the market, so like in the same way that the ML market is not as big as the software. Everyone's heard of software engineering, even my mum. Most people these days have heard of ML and AI. Not necessarily my mum, but hardly anyone's heard of RL, and it's because the application of RL is probably a bit smaller than ML in general. Therefore, it's applicable to a smaller number of applications. But with that said, I do think that we're not at that point yet. There's definitely a gap between what is possible and what we're doing at the moment. Bottlenecks. So I think it just comes down to understanding, knowledge, the application of these things. But then on a technical level, it's probably, I think, simulation. In fact, here's one thing. I think that the current problem is that it is technically possible now, but it's quite difficult to learn models. I think that's the future of RL actually, is learning models, learning simulations. At the moment, simulations are still very hand-coded. They're created by humans according to physical rules. But I think that there's a potential for us to be able to learn a simulation or learn a model effectively from log data and then use that as our simulation. And that already exists to a certain extent. It's using like variational autoencoders to generate and then we can apply random noise to the output of that to generate new scenarios and use that as a simulator. So yeah, I think we're getting there. But once we get an ability and a framework and some code to be able to basically create and learn a simulation for any data, I think that would be really powerful, because then you can really truly do your development offline and be not guaranteed, but you could be much more certain that you've got a really good model before you actually start trying it in real life.
So it's like using reinforcement learning for training reinforcement.
Yeah, it's a bit meta. Yeah, well, in fact, there is meta.
Counts, right?
It's learning how to learn optimally. So it is a subject. It is an academic field. Yeah.
But can also be like these, adversarial networks. Crazy people who jump in front of cars or things like that.
Yeah, exactly.
Simulation.
That's part of it. Yep.
So we still have 2 more questions. Can you elaborate on feasibility of reinforcement learning for strategic business decisions like pricing strategy, launching different product features, which customers to contact, and so on?
Do you say visibility? Sorry. What was the start?
Feasibility, like
feasibility.
Yeah.
Okay. Yeah. That makes sense. Yeah. I think all of those are applicable. The answer is yes. Yeah, very feasible. Anything that you can imagine performing multiple experiments to arrive at an optimal value, that is a great application for RL. Like, I think most of the research and most of the work so far has been done in not pricing, but the other end of the spectrum, the bidding. There's been a lot of research in bidding, so attempting to control and constrain like advertising budgets, for example, to be able to bid in an optimal way. So there's been a lot of research into that, but I can easily imagine that if you had a large volume of sales, so you're coming from the other direction, if you're setting the price, you could also use RL to set the optimal price, which will probably change over time. And in fact, there's many companies that attempt to do this for, like, Amazon prices and OLX prices and things like that. But I think RL has the capability of making that a bit more sophisticated. Like, if I go and look on, there's a famous, I don't know if it's around the world actually, but in the UK there's a website called Camel, which is probably the best name for a website ever. But it tracks Amazon prices, and so you can see the history of the best price in Amazon, and it's really jagged. It's like some of the algorithms that are used to set these prices are really, they're not there's no finesse to them. It's basically fix the price there and fix the price. There's got to be some better algorithm, like an RL based one, that is able to set prices a bit more intelligently.
Okay, so we need to wrap up. We have one more question, but I think they are pretty short. So first question, you probably get it regularly. Are you hiring? And if yes, what kind of people you look for?
Yeah, send me an email. Yeah, I mean, we do a lot of work, consultancy, generally more in the ML space and the RL space at the moment. But I'm hoping that we will. I'm hoping that the future is quite bright for RL. So yeah, just get in touch over email.
Yes, and the other email is related. Hey Phil, are you available? And what's the best place to contact you for an additional 30 minutes talk?
Yeah, definitely, 100%. And just contact me, winderresearch.com, Phil at winderresearch.com. Details on the slides.
And I did share the link to the book, and probably there is information how to contact you.
Yes, exactly. Yeah.
Okay.
Perfect.
Thanks a lot.